everyone, my name is Danny, and today I'm going to be telling you about my 6881 final project, which is non-prehensile paper folding. What this looks like is that we start with a piece of paper, which is affixed on one edge to this platform and hanging off the edge of the platform on the other side. We want to use this sphere manipulator, shown in red, to push the paper up and over to its other side. And presumably, we could then use some other manipulator, maybe a similar non-prehensile manipulator, to flatten out this edge and create an actual crease and actually fold the paper. This video shows me doing the task with my finger. And the idea is that by restricting to non-prehensile folding, we make it so that the problem actually has to contend with the paper's dynamics, versus using a gripper, you could just grab one end of it and move it without really having to think about any of these constraints other than maybe not ripping the paper. Let's talk a little bit about how I modeled the system. Unlike a rigid body, which is fairly simple to simulate, a deformable object like paper requires some level of simplification to be feasible to model in simulation, unless you're going to use something like an FEA program. So what I ended up doing is modeling the paper as a series of rigid links, in this case 20 rigid links, which are each connected by a virtual torsional stiffness and damping. So the torque at each joint is proportional to the angle deviation from zero and then also the angular velocity, and this gives some behavior that is roughly similar to paper. The manipulator is basically what we used in the non-prehensile examples in class. It's just a sphere which applies force in the X and Z directions. The first controller that I tried is a PD trajectory tracker. What this means is that there is a nominal X position and nominal Z position, and the force applied in each of those directions is proportional to both the error and then also the derivative of the error, and these are determined by constants that are set. But I wasn't able to make this control system actually complete the task. Sometimes the manipulator would not go high up enough and would get stuck under the paper, as shown in this video. And then sometimes the manipulator would go too far up and then the paper would fall out from underneath it. Something to note is that this isn't really physical. You don't normally have paper bend back on itself and then just sit there. So this is a bit of a simulation error. That being said, ideally we would have a controller that is robust to errors like this. Another type of control that I tried is an optimization-based controller. The way this works is I formulated the controller as an optimization problem, where the decision variables were the body poses, velocities, and acceleration, as well as the time steps in between each time the control was applied, and then also the forces applied by the manipulator. The constraints are the dynamics of the system, and then using an Euler method to step forward in time and relate the states at different time steps, and then the initial and final positions, where the final position is making sure that the last link is somewhere on that platform and the manipulator is pressing it down. Unfortunately, I wasn't able to get this optimization to solve. It's possible with some amount of tweaking that I would be able to get this to work, but it's not super surprising because this is a complex system with a lot of state and nonlinear dynamics. So on one hand, if I had been able to get the optimization to work and be able to benchmark it against other control options, that would have been great. But ultimately, the system itself is a little bit brittle and not really robust to changes in the system anyway. So there are other reasons why it's not ideal. It also relies on full state feedback on the body poses, velocities, accelerations for all of the bodies, which is not ideal. This brings us to what I'm going to call the edge controller, which essentially just relies on the state of the last link. The way that this works is that the forces applied to the manipulator are decomposed into the force that is normal to the last link in the paper and parallel to the last link in the paper. In the normal direction, we apply a constant force, and in the parallel direction, we have just a proportional controller to maintain a set distance from the edge. The idea here is that when you try to do this task physically, you're essentially just going to continue pressing with your finger a certain distance away from the edge, and that's all that you really have to do. And this actually bared out in simulation and was able to complete the task. Just to talk a little bit about the conclusions and next steps, some of the next steps would be a little bit too in the weeds of the simulation for this video, but one conclusion is that it seems like the pose of the last link, so the edge link, is sufficient to be able to complete this task. It's sufficient information to give a controller to be able to complete this task. However, there are issues with the simulation being non-physical. This plot on the right shows essentially what we saw in one of the options with the PD controller, where the paper flops down when instead it should spring back. In any case, this project was really fun, and I want to say thank you all for listening to my presentation.